I want you to imagine the near future of electric mobility and energy storage as a single coherent story where three technology families, sodium-ion cells, solid-state batteries, and magnet-free motors, are not isolated breakthroughs, but parts of a larger system redesign that changes how cars, homes, and grids behave, how factories are organized, and how geopolitics and supply chains breathe easier because dependence on a handful of scarce materials finally relaxes. And that's what I'll talk about today on Knowing is Winning. The first thing that becomes obvious when you look at magnet-free motor research is that engineers stopped treating magnets as sacred, immutable ingredients of traction motors and started asking the deeper question: how do we make the same torque, efficiency, and power density without relying on rare earth permanent magnets with their dirty mining footprint and fragile supply chain concentration? Teams in industry and academia converged on three coherent responses: advanced electromagnetic excitation schemes that substitute active coils for permanent magnets, redesigned induction and switched reluctance topologies that recover efficiency with better control, and novel magnetic materials that avoid rare earths while trading off performance in ways manufacturers can handle with clever cooling and power electronics. Those responses are already in vehicle-grade prototypes and supplier roadmaps, not only in papers, because the automotive industry realized that resilience of supply is as important as peak performance. There is an elegant complementarity between magnet-free motors and the new battery chemistries. When you remove rare earth magnets and you slightly shift trade-offs, motors can weigh a little more or require different cooling, and battery designers answered with chemistries that prioritize safety, low cost, and operational envelope rather than obsessive energy density per kilogram alone. This is where sodium-ion cells re-enter the conversation as pragmatic, industrially achievable alternatives that excel in cold climates, quick charging, safety, and scalability because sodium is abundant and geographically widespread. Sodium ion is not vaporware. Large manufacturers have progressed from lab cells to pilot and early commercial lines and are explicitly positioning sodium ion in niches where its strengths matter the most: grid and stationary storage, affordable urban and two-wheeler mobility, and even mainstream EVs where packaging and vehicle architecture can accept slightly lower volumetric energy density for big gains in cost, robustness, and life cycle environmental impact. Firms that once ignored sodium are building factories, opening demonstration megawatt scale storage projects, and signing OEM partnerships, so this chemistry is moving from curiosity to industrial option with concrete supply chains and policy attention. At the same time, the solid-state battery trajectory answers a different human desire: lighter packs, higher range, faster charging, and far greater intrinsic safety. Multiple technology routes, polymer electrolytes, ceramic oxides, and sulfide electrolytes, are all being piloted by major players, with pilot production lines already operating and small batch vehicle integrations targeted in the next few years. The result is not an instant replacement of existing lithium-ion plants, but a multi-track industrial evolution where manufacturers layer new cell types into vehicle portfolios: sodium-ion for cost-sensitive or cold start segments, liquid lithium variants for current mainstream models, and solid-state for premium, long-range, safety-critical applications. These three families, sodium-ion, solid-state, and magnet-free motors, begin to look like elements of an architectural playbook. A low-cost urban EV with magnet-free inductive motors and sodium-ion packs can deliver durability, cold weather resilience, and a lower total cost of ownership, ideal for fleets and emerging markets. A premium EV with all solid-state cells and a highly optimized permanent magnet or electromagnet rotor can chase maximum range and rapid charge. Vehicle platforms will be designed to accept modular battery modules and different motor types, so OEMs can apply the right tool for the job without re-engineering the whole car for each chemistry or motor topology. Because sodium-ion and some solid-state variants favor intrinsic safety and tolerate a broader temperature range, they reduce the need for heavy thermal management systems and complex battery BMS strategies in many use cases, and that has cascading effects. Packs can be simpler, cheaper to service, and recyclable with fewer hazardous materials, which reduces life cycle costs and regulatory friction for second life and recycling programs. What does this mean for the factory floor and industrial logistics? It means two shifts. First, manufacturing becomes more modular and material aware. Lines are being retooled not to produce a single cell type at scale, but to switch between chemistries to add processes for solid electrolytes or to install high temperature calcination for hard carbon anodes used in sodium-ion cells. European and multinational consortia are already designing production flows for quasi-solid and polymer-based sodium cells intended for residential and grid storage, signaling that manufacturing IP and equipment suppliers are adjusting to multi-chemistry realities. Second, supply chain geography changes. Sodium raw materials are locally abundant almost everywhere. There is seawater or salt deposits all around us, and that gives governments options to onshore parts of the value chain, which in turn reduces geopolitical leverage points that previously accrued to lithium refinement hubs. From a consumer perspective, the narrative is visible in three everyday ways. One, you will see more vehicles that promise fast charging in cold weather without dramatic battery degradation, because sodium-ion formulations hold chargeability under low temperatures better than many lithium chemistries. Two, you will see more energy storage solutions for homes and communities priced to compete with grid upgrades, because sodium-ion and quasi-solid designs target cost reductions per kilowatt hour while delivering reliable cycling for renewable buffering. Three, you will see EVs with comparable performance but lower sticker price in certain segments, because OEMs can design the vehicle to balance energy density with structural and packaging choices, rather than chasing energy per kilogram as the only metric. The motor story amplifies these consumer benefits. Magnet-free motors, especially the inductive excitation and refined switch reluctance topologies, reduce dependence on neodymium and diprosium while delivering competitive efficiencies that are good enough for mass-market cars and excellent for commercial vehicles, where robustness and cost matter more than absolute peak power density. Automotive suppliers are already publicizing prototype units and supplier awards for magnet-free designs, and that of course translates quickly into supply chain decisions. Fewer rare earth imports, more domestically producible copper and steel, and an ability to weather price spikes in critical minerals. The environmental argument is straightforward but powerful. Mining and processing rare earths or high-grade cobalt and nickel has heavy social and ecological costs in concentrated locations, By sharing the technical burden across alternative magnet designs and diversified battery chemistries, we lower systemic extraction intensity and create more opportunities for circularity, because cells built from abundant materials are easier to recycle and revalue locally. However, there are real engineering trade-offs and practical constraints that keep this story honest. Sodium ion still lacks the best lithium chemistries in energy density per kilogram, which means architecture and packaging must adapt. Solid state remains challenging at scale because solid electrolytes require new manufacturing environments and interface engineering that has only recently started to clear some of the biggest bottlenecks. Magnet-free motors tend to weigh more or require stronger cooling and more sophisticated inverters to match the control finesse of permanent magnet machines, and those factors produce interesting system-level design choices where battery, motor, and chassis teams must co-optimize early in the vehicle program rather than treat each subsystem as an add-on of sorts. The industrial response to those constraints is pragmatic: multi-path roadmaps. Leading battery OEMs and car makers are not betting everything on one chemistry. Instead, they're layering sodium-ion production lines alongside continued investment in high-energy lithium and aggressive pilots for solid state, coupling that with powertrain designs that accept a range of motor types so the vehicle program can match the best local supply and application economics rather than be hostage to a single technology hypothesis. Policy and standards are moving in parallel, which is crucial. Governments are funding pilot lines, convening standard bodies for solid-state safety testing, and underwriting consortia focused on domestic supply chains for non-toxic, abundant battery materials. Those policy signals accelerate investment by reducing regulatory uncertainty around safety certification for new chemistries and by offering industrial incentives to build manufacturing capability near demand centers. There is a second, less obvious effect: new aftermarket and service models. Batteries that are safer, cheaper, or more robust enable novel service propositions. Battery swap fleets using sodium cells, community energy services that install and manage sodium-ion storage for microgrids, or modular solid-state packs that can be leased for short-term, high-range needs. Motor repair and rewind shops that once specialized in magnet replacement will need to pivot to electronics and cooling service for coil-excited rotors, creating a wave of retraining opportunities for suppliers and technicians. For startups and investors, the combined narrative is fertile. Materials suppliers for hard carbon anodes and stable polymer electrolytes, equipment makers that can run humidity-controlled lines for sulfide electrolytes, power electronics firms that improve inverter control for magnet-free motors, and software teams that co-optimize thermal management across motor and pack all look like compelling bets because they sit at the intersection of multiple trends rather than depending on a single winner. On the user experience side, the payoff is both subtle and tangible. Imagine an urban delivery van that charges to 80% in under 20 minutes in sub-zero temperatures, operates for years without dramatic capacity fade, and returns to the fleet yard for a standardized module swap rather than a long out-of-service repair. Or imagine a rural microgrid where local salt resources help keep storage costs low, enabling households to run cheap daytime air conditioning and sell surplus to the grid with minimal dependence on imported minerals. These are not science fiction scenarios. They are the explicit business cases companies and consortia are pursuing today. There are geopolitical consequences too, of course. Diversifying battery chemistries and motor designs erodes the leverage of single-source material producers and distributes economic opportunity more widely. Countries with abundant sodium resources or advanced manufacturing capabilities can carve a niche in energy storage and EV ecosystems without having to develop giant lithium processing industries overnight. That redistribution of industrial opportunity makes electrification more inclusive and less geopolitically fraught. Technical timelines remain compressed enough to be meaningful in this decade, but staggered enough to keep markets rational. Sodium ion is already in limited mass production in specific markets and is scaling. Solid state is entering pilot and small batch production with promises of broader adoption toward the end of the decade. Magnet-free motors are appearing in supplier portfolios and selective OEM programs today and will broaden as inverter and control costs fall and manufacturers accept slight packaging compromises for supply security. In terms of investment and procurement signals to watch for, the early indicators of genuine maturity are pilot factories converting to gigawatt-scale lines, OEMs committing vehicle models to a given chemistry for multi-year production, and standards boards publishing safety and testing frameworks for new electrolytes or cell constructions. Those actions convert lab promise into bankable industrial paths and tend to precede visible consumer products by a predictable margin. The engineering culture change this triad fosters is important. Cross-disciplinary teams that once argued over whether to prioritize energy density or motor torque now design vehicles holistically from mission profile down to material sourcing. The best design houses are reorganizing to co-optimize electrochemistry, thermal architecture, power electronics, and motor topology from the earliest concept sketches rather than in discrete silos, and that cultural shift accelerates the practical integration of sodium ion cells, solid-state variants, and magnet-free machines into coherent platforms. If you wanted a single sentence that captures why this matters to an everyday person, it would be this: these technologies together make electrification more affordable, safer, and more resilient by reducing dependence on a narrow set of inputs and by creating multiple complementary engineering paths to achieve useful performance in real-world conditions. Finally, what should a curious viewer take away? Pay attention to product announcements that reference chemistry names explicitly. Look for OEMs that announce specific pilot vehicles using sodium ion or solid-state packs. And notice supplier awards and standards milestones. Those are the practical signals that laboratory advances are moving into the market where they will affect price, availability, and performance for ordinary buyers. The transition itself will not be a single technology switchover. It will be layered, pragmatic unfolding where each innovation reduces risk and expands choice. And that is exactly the kind of systemic progress that wins over time. And this was Knowing is Winning. Thank you very much for watching.